Swayam Prabha. Digital India. Educated India.
Welcome you all to the next class on Inorganic Chemistry of Life, Principles and Perspectives. So, in the previous class we have looked at reductase, dinuclear cases and ribonuclear reductase, and also we have looked at the ributrin, which is which decomposes the H2O2 to water. Both of these have been looked at. So, having looked at some reductases and we have looked at already oxygenases, now probably it is a logical to get into some hydrolase or phosphate hydrolysis, which is known as phosphatases. So, these are one of the things reasonably well understood or called purple acid phosphatase. Why the term purple? So, the purple comes from the color, acid from the pH. So, acidic condition. So, these are purple acid phosphatases, and these are of course the metal enzymes which are involved in hydrolyzing the phosphate esters under acidic conditions. And and if you look at their oxidized form, they are in purple in color, and particularly so because you have the color is coming, the origin for the color is the charge transfer, and the charge transfer is from the tyrosine to the ion center or oxidized ion center. So, these are the kinds. And if you look at the centers of these, they are all composed of iron 3 plus, and the second metal ion could be iron 3 plus, could be zinc 2 plus, could be manganese 2 plus or magnesium 2 plus, and these are all found in different kinds of species. So, and the iron 3 plus of course is the one which is conserved in all. The second metal ion is being replaced either by zinc or by manganese or by magnesium or by iron 3 plus 2. Okay. So, generally when you take this purple acid phosphatase and try to use a mild reducing agent, they get into active form. So, that means active form has some reducing, but if you use a strong reducing agent, then they will break down these dinuclear centers, the dissociation takes place, enzyme becomes inactive and the solution becomes colorless. So, that means they are totally broken down. Okay. So, these are enzymes which are involved in hydrolyzing the phosphate ester bond, etc., etc. And I said they are dinuclear, one of them is iron 3 plus, other than could be either the iron 3 plus, magnesium 2 plus or manganese 2 plus, or any of these things are possible depending upon the type of species. Now, let us look at some other species which are, let us say, eukaryotic species and the higher level which is mammalian. There is a large proportion of the overlap of the amino acid between the eukaryotic species for purple acid phosphatases and mammalian purple acid phosphatases. On the other hand, if you try to look at the plant based purple acid phosphatase with that of the mammalian purple acid phosphatase, there is a large difference. There is only 20% of the overlap you will find. So, between the eukaryotes and the mammalian, there is a huge percentage of overlap of the amino acids and the sequence homology, which is 70 to 80%, whereas there is only 20% of the sequence homology when you compare the purple acid phosphatases between the plants and the mammalian. Just like we have used the short form RNR for ribonucleotide reductase, let us use the short form of the PAP, purple acid phosphatases. Okay, again if you look at the metal centers of these ones, between the plants and the mammalian there is a difference. So, mammalian PAPs been isolated and purified to this point, have been composed of iron, where in the plants the metallic nucleus is composed of the iron 3 plus and either the manganese or the zinc, and that is where the difference comes, diversity. So, the second ion in mammalian, second metal ion is in mammalian is still iron, and in other kinds of things it changes to zinc and magnesium and manganese too, and mostly found was zinc and manganese in case of the plant things. So, we have tried to look at the compositional metal ion compositional aspects, and we also looked at the protein overlap, amino acid overlap. So, this eukaryote and the mammalian has a large overlap of amino acid, and there is a very little overlap between the plant and the mammalian one. And the greater difference is that the dinuclear center is primarily iron 3 in case of mammalian, and in case of the plants it is iron 3 and magnesium or manganese or zinc. So, mainly zinc and manganese are being found. So, we got some reasonable amount of introductory aspects of the purple acid phosphatase, purple coming from the color in the oxidized form, acid coming from the acidity of this medium, and the phosphatase activity is the hydrolase phosphate ester hydrolysis of this one. So, therefore, these are very well understood, purple acid phosphatase. So, you can see the reaction here, this is the phosphate ester and this is hydrolyzed to the alcohol and phosphate. Okay, HPO4 2 minus is a phosphate counterpart and the alcohol counterpart, and when you condense them you will get the phosphate ester, and this is what is happening. So, therefore, as I said that you have the purple acid phosphatases having both the iron center or iron with some other metal ion, it could be manganese or it could be zinc. So, you have shown both the cases. The enzyme is shown over there, you have different units connected together, and then you have the activity going on at every dinuclear center is catalytically active. Whether this is a iron dinuclear center or iron M2 plus dinuclear center, where M2 plus is zinc 2 plus, manganese 2 plus, in some cases magnesium 2 plus too. So, all of these. Now, let us look at the iron. You have 2 histidines on one side and on the other side one histidine we have already looked at, and a tyrosine. So, this is the tyrosine which is involved in the charge transfer transition that is happening, and this is again conserved when you go to this. The iron and the zinc has got a very similar kind of a binding centers, and therefore, the iron center is preserved. Therefore, the purple color is still retained because of the tyrosine to the iron 3 charge transfer transitions. So, there is the core, iron core is very well preserved in spite of the amino acid sequence may have a greater overlap or may have a lesser overlap. Something like 70-80% of great overlap or 20% of the overlap, in both the cases is there, except that the second iron center is replaced by the zinc center in this particular case. So, you can take this from the plants or other non-mammalian and mammalian kinds of things, but the reaction is the same. Okay? And the 2 aspects that we have stressed now, one is the purple color, the other is the oxidized and the reduced forms of this. Let us try to understand this, how one studies this purple color, how one studies this oxidized and reduced forms of this, particularly when you take the mammalian case. Now, as I said already, the purple color is coming from the LMCT, ligand to metal charge transfer. So, this is basically ligand to metal charge transfer is called. I talked to you in much early stage in this course. So, this is ligand to metal charge transfer. So, in this case the ligand is tyrosine is ligand, and iron 3 of course is the metal center. Okay. So, that is where we have ligand to metal charge transfer, tyrosine to the metal charge transfer. Okay, this charge transfer can be really recognized One is by looking at the absorption spectrum, where you have a charge transfer spectra. Certain times these charge transfer band will also overlap with other bands, therefore, you will not be able to make out. In such a case, you can use a vibrational spectrum, not a simple IR vibration, not a simple FTIR, but you need to look at the resonance Raman spectrum. So, RR is referred to resonance Raman spectrum. So, what is Raman spectrum? We know that it is vibrational. Those which are not found in the IR will be found in the Raman spectrum. We know all that. Now, what is the resonance Raman? So, the resonance Raman is the one where the Raman spectrum is measured under a resonance. What kind of resonance? The electron transition. So, electronic transition. So, you electronic transition. So, how would you get the electron transition? If you know the absorption band, you can excite the sample at that particular wavelength. So, in this case, there is a absorption band at 514.5. So, suppose now you measure a Raman spectrum while exciting the sample at the 514.5 nanometer, then what you get? You get a Raman spectrum which is the vibrational Raman spectrum which is coupled with this transition of the electronic transition. So, therefore, you have a electronic transition. So, this coupling with the vibrations. So, that is what you have in this. So, when it couples, what will happen? The vibrational bands will become highly intense. So, when they become highly intense, you measure once the spectrum without this excitation, you measure the spectrum with the excitation, you will see the bands which are enhanced in the vibrational bands. So, from the enhanced vibrational bands, you can find out the coupling that is there between the tyrosine and the neighboring. So, that is what is basically done in this case. So, this the purple acid phosphatase and the pink iron phosphatase, they are all seen, as you can see. The bands corresponding to the vibrational bands in that vicinity are identified to be the enhanced one. So, from this basically you can get the tyrosinyl vibrations, and then talk that there is a tyrosine bonded to the ion center and there is a charge transfer too. Okay. So, understand the resonance Raman is the Raman spectrum under the electronic excitation being continuously pumped in, and in this particular case 514.5 nanometer, because the absorption takes place at that, and so therefore, in the tyrosine to LMCT, and this will enhance the tyrosinal vibrations. Okay. So, coupling with the vibrations, and this leads to, when it coupled, it gives the enhancement and in the coupled vibrational intensity. In other words, the intensity of those coupled bands will be increased, so that from that we can understand this. Now, let us look at the reduced forms, the oxidized form, etc., etc. You can see that this we are of course referring to the ion-ion case. The ion-ion case, there are two ions are there, and oxidized form and then into the reduced form too. So, in this is the heteroferrin, which is for the mammalian case. So, mammalian purple acid phosphatase will have both the metal centers as the ion. So, in this case you can look at the purple acid phosphatase at the 4.9 pH, which is acidic pH, and if you look at this particular EPR spectrum, you can see the EPR spectrum is very characteristic of the rhombic type, as is equal to half, with the antiferromagnetic coupling of the with the S2 S is equal to. Okay. So, the one center and the other center, say, which is S is equal to half, other is S is equal to 2, and that is where you have the coupling happening in this. So, that coupling can be identified from this EPR spectra, but in this particular case you do not need to really know fully well how to analyze this, but just the taking into consideration that is what is happening with these ones. Okay. And that is why you get the extra bands because of coupling of this. Now, you can also look at their proton NMR spectrum. Okay. So, proton NMR spectrum, and you have there are two of these are looked at, the pink state and the purple state, and the purple state is the completely oxidized state, and the pink state will have the reduced also in that. In this, the spectra were measured in water and with the D2O exchange to find out those groups which are exchangeable. And you see this particular resonance or peak is disappeared when you add the D2O, and that means that is the one where you have in the vicinity of the metal center. And all of these are very much shifted, and you see in this purple case oxidized, you do not see much of a splitting kind of thing, everything is broadened. And in the pink form with one of the center being reduced, then you can still see but shifted. This is called contact shift, and these are going up to 100 ppm, etc. In a proton NMR, going to beyond 15 ppm is nothing but the paramagnetic shift or contact shift, and this is the contact shifts. So, therefore, one can identify the tyrosine, that the charge transfer bands, the oxidized reduced couplings, etc. All of these can be identified by the EPR, and the proton NMR we have already looked at in the earlier case. The proton NMR, you can have a contact shifts, you can have a broadening of these, all these we have looked at. And the proton to water to D2O, some of the protons will be exchangeable, and those protons can be identified. So, therefore, their connectivity with this. Now, we looked at the general aspects of the purple acid phosphatase and the purple color, the transition and oxidized reduced form. We looked at the comparison between the mammalian versus the plant, mammalian versus the other kind of organisms where the purple acid phosphatases are present. Now, let us look at what is the role of these metallic center. So, and here we have iron, the second metal is, let us say, M, and what is the role of this, and we have already seen this center which is very well known. Now, this particular thing is involved, see, to have a reactivity, what is required? This particular phosphate ester must be cleaved at this stage, so that you get a hydrox alcohol and the phosphate moiety. Okay. So, for that obviously you need to have a binding followed by the hydroxyl attack or nucleophilic attack or water attack on these ones, and that is what happens. So, therefore, you have the phosphate ester OR is bound to the one of the metal center, and the other metal center in the active form there will be water converting into the OH, and this OH is involved. So, that is why we are saying that the activity starts in that, and this OH is in proximity to the phosphate ester, and that will bring a nucleophilic attack. And another aspect you should notice here is this phosphate ester is having secondary interactions through this, one other histidine, another histidine, etc. So, what do you call this? These secondary interactions will basically recognize the phosphate ester and orients the phosphate ester. So, the phosphate ester has to be oriented in such a way that this binds to the metal center, and the phosphorus center is in the close proximity. So which is within the range of 2.5 to 3 angstroms. So therefore, you can have a nucleophilic attack taking place in this, and that is what precisely happens. So you can you have hydroxyl which is reacting with this. So and the phosphate ester binding to one of the metal center, the other metal center will provide the nucleophile. So therefore, one is at a kind of a substrate binding, or is the catalytic. So you can say, so within the same binuclear center, one acts as a substrate binding, other acts as a catalytic center, both together. So we can say this is the structural kind of a one, and this is the catalytic one. So and this provides the hydroxyl attack, and during the hydroxyl attack you will find the intermediate where the the intermediate where this phosphorus center with the 1, 2, 3, 4, 5. You know this pentacoordinated or pentavalent phosphorus center. So pentavalent phosphorus center is a transition state kind of thing. And so attack on this. Now that will be further breaking this particular group and leaves out this particular OR going out, and for these the proton sources are coming from these particular residues. So therefore, there is a one is these residues are helping in recognizing the phosphate. These residues in the neighbor are also helping protonation deprotonation aspects too. So therefore, secondary interactions in an enzyme or metalloenzyme are also very important. It is not only primary where the metal ion is bound, the secondary interactions are also. So that will give the ROH out, and then H minus will give. So you can have, so in presence of the phosphate you can go back, phosphate ester you can go back this too. Okay. So you can see, so one is the binding, other is the nucleophilic attack and transition state, and then further hydrolysis and breaking the alcohol, and the next step is replacing the phosphate moiety by the incoming phosphate ester. So we have not shown the other part. Now if there is no incoming phosphate ester, then you can add water, the water will displace and will come that one. So we can do. So this will be continuously happening, so that is why it is shown over there. Okay. Phosphate ester binding, the transition state for the hydrolysis of this, and the ROH going out, and the entry of the phosphate ester replacing the phosphate moiety HPO4 2 minus moiety. So this is continuous, and you can see one of that particular intermediate kind of the binding center can be seen over there. Okay, and this is the center. So now we understand the purple acid phosphatase is a hydrolytic kind of a activity, and there is no redox activity involved. So out of the two metal centers, one metal center is involved in the binding, the other metal center involved in providing the hydroxide, and then stabilizing or favoring through the formation of the transition state, and then the water attack, and then those things. So and the secondary these groups are involved in the protonation recognition as well as the protonation deprotonation steps in this too. Okay, so this comes to one of the aspects of this hydrolysis parts of it. Then we also have some reductases where the reductase is not by the binuclear ion center, but these are by the heme reductases. So we have already looked at the non-heme reductase. Which is non-heme reductase? Ribonucleotide reductase itself is a non-heme reductase, because the two ion centers which are present are no heme is there in this. So we will look at in this particular case the reduction of NO2 to NO nitrite reductase, as well as NO2 to NH3, where you require more number of electrons, and for nitrite to nitric oxide you require only less number of, because you are removing only one O. In the other case you are removing both the O's and putting hydrogens, and therefore making into ammonia. So these are the two cases we will look at under the under the heme reductases. Okay, let us take the first part is the nitrite reductase in this. The nitrite reductase uses the two the CD1 cytochrome oxidase contains, there are two types of hemes are present in this, not one heme. Just like in the dinuclear center, two ions are the di-ion center, two ions are there. In this particular reductase, the two hemes are there. So, one of the heme is the C type of the heme and the other heme is the D type of the heme. And it is the C type of the heme which is involved in the electron transfer, it is the D type of the heme that is involved in the catalysis of this. Because you require electron transfer, you require to remove one of the O and you require to make the NO in this. So, the once it is reduced, the reduced D heme binds to nitrite because it is a catalytic center and converts into the product. And whereas a cytochrome C nitrite reductase is a multi-heme enzyme that will convert the nitrite to ammonia, and this we will see in as the next example. So, the active site of the ion is bound to the protoporphyrin 9, okay, and that is covalently linked to the enzyme proteins. Okay, so, you can see that there are the two types of ion. Let us look into this one. The two types of hemes, one is the C heme type C, heme C we already studied, and then heme D type which has a different kind of a groups. So, here you have a reactivity is going on catalytic, and here only electron. C heme is involved in the electron transfer while D heme is involved in the catalytic reaction. Okay, so, you can see that this we will come back to that. The nitrite is bonded, there are two histidines are there, involvement of that, and this is the bound site with the D, and these are the other residues providing the electron transfer, etc. So, we will look at the detail in a different context in the next slide. There are two histidines are involved in this particular thing. And in the conversion of nitrite to NO. So, it is the at the heme D1 site, the histidine 327 and histidine 369 are absolutely essential for substrate binding and also to ensure the catalysis is confirmed. And how do we know? Because if you replace any of these histidines and both the histidines by other residues, which is called mutation, no reactivity, no the conversion and release is not happening. Primarily because in such cases the conversion takes place to some extent, but release will not take place. Okay. So, there are some two distal histidines also play important role in catalysis, and therefore, all these things are important for these complex formation, binding and then conversion. So, if you look at the whole enzymes and the mutant reactivity, there is some new side chain in the active site which is involved, which is important, and there is some the tyrosine, the density is reduced in that, it just moves with the N-terminal arm. So, that means there is some protein conformational change happening, and there is also some topological changes in the C design domain. So, that means there is electron transfer happening in this area. During the electron transfer, we have already seen that the reorganization occurs, and that is what we do. So, this whole thing. So, the two invariants histidine plays a very crucial role in the reactive activity, and structural organization. There are two things are there. So, there is a structural organization, reorganization where the electron transfer, and in the other case we have the binding and reactivity. These are the two essential aspects of it. So, now you can see the structure, the cytochrome C D1 in the oxidized form. There is a helical C type. So, you can see these are all the helices, and there is a C type, this is a C type, and this is sitting on the top, and the D1 is sitting like the 8 bladed propeller heme binding ones here. There is one, and there are the propellers. So, the C part of it and the D part of it, and they are one over the other. Okay, so has the C has got histidine 17 and histidine 19 as the actual ligands, which you cannot see so much over here, and the D case you have 200 and tyrosine 25 close by. So, the overall structure of a mutant, when you look at the tyrosine to the cysteine variant, is essentially identical to that of the wild type enzyme, with small difference only in the vicinity of the mutant case. So, histidine coordination, the heme C is obviously retained there. So, but the D1 heme is actually ligated by 800, and when you make the mutation, because you are changing the tyrosine and then it picks up in the solution the sulfate moiety. So, that means we can understand that this group, this metal center has an anion kind of a affinity. So, we will see more details of this enzyme cytochrome C oxidase for the nitrite reductase in the next class, and we will also look at the continuation of that going from nitrite to ammonia too. Thank you very much.